Welcome back for a new lesson from Alientech's diesel training course. Today we will talk about the fuel control strategy of older generation diesel engines. We will analyze how the engine control unit manages the flow of fuel and air to be injected, and how it manages the exhaust gas recirculation. Let's not waste any more time. Let's start with the fuel demand generated by the driver. The external fuel request is performed via the accelerator pedal, based on how far the driver presses the pedal in terms of percentage and the engine speed. The engine control unit coordinates a higher or lower request of fuel. The fuel requirement maps, also called driver wish, are those maps that convert the signal of our potentiometer placed on the accelerator pedal into a quantity of fuel to be injected. Therefore, for all intents and purposes, the request for fuel starts from the driver via the accelerator pedal. Another condition of external fuel request can also be performed by the cruise control. When we set the cruise control, we do not press any pedal, but we set a speed. Consequently, the engine control unit will make a request for a specific amount of fuel for the vehicle to reach or maintain the set speed. Curiosity. The torque and power instantly generated with cruise control is a more comfortable, non-aggressive demand for performance than that performed via the accelerator pedal. Let's analyze a fuel required in standard conditions map. In this map, the values present are expressed in milligrams of fuel to be injected for each cycle, as a function of the speed and the percentage of the accelerator pedal pressed. We can immediately notice that the manufacturer has already foreseen the amount of fuel in the event of high engine revolutions or a high accelerator pedal percentage, which can be translated as high performance required. Conversely, when the engine revolutions or the percentage of accelerator pedal depressed are at idle, the engine control unit reduces the amount of fuel to be injected to provide lower performance. Let's take a look at an example right away. Let's use as a reference 2,499 engine revolutions at 85% of the accelerator pedal pressed. We find a value of 35.40 milligrams of fuel injected. This means that at that engine speed and at that percentage of pedal pressed, the engine control unit requires 35.40 milligrams of fuel to be injected for each cycle. Now, it is necessary to check whether the manufacturer has foreseen a limitation of fuel to be injected in order to limit the performance of the vehicle. To do this, we need to analyze the fuel quantity limiter map. The map in question indicates the quantity of fuel to be injected for each cycle, as a function of the hectopascals measured by the APS sensor and the engine speed. Thanks to these maps, therefore, we understand that the manufacturer has actually limited the amount of fuel. In this case, it is sufficient to substitute the values within the map with the new higher values that we found in the previous map, allowing you to inject higher quantities of fuel and consequently have higher vehicle performance. At this point, the engine control unit converts the amount of fuel to be injected into values for the actuators. I'll give you an example. Let's say that the engine control unit controls 40 milligrams of fuel. It will have to convert this value into injection advance values, which for diesel engines is controlled by the injection timing map. Let's take a closer look at this map too. Depending on the amount of fuel to be injected for each cycle and the engine speed, the map contains values expressed in degrees of the crankshaft, which determine the relative angular crankshaft degrees, taking into account the position of the piston with respect to the top dead center when the injectors must be open to inject fuel. Negative values are intended as delays. Therefore, it means that the injection will take place after the piston has reached its top dead center. The positive values are intended as advances, meaning that the injection will take place before the piston has reached its top dead center. Furthermore, the engine control unit, in addition to the amount of fuel to be injected, must control the air pressure inside the intake manifold to have a sufficiently lean carburation and prevent black smoke in the exhaust gases. To do this, another map, called turbo pressure, comes to our aid. Let's take a closer look at this map. In this map, the values present are pressure values expressed in hectopascals, as a function of the engine speed and milligrams of fuel to be injected for each cycle. Also in this map, we see that as engine RPMs and fuel injected increase, the pressure inside it rises, reaching a maximum peak of 1,950 hectopascals. This indicates the maximum value that this turbine can reach, using the original file. We have seen the check that the engine control unit carries out in order to control the fuel to be injected. However, the engine control unit will also have to properly calculate another very important element: the nominal air mass per cylinder. The nominal mass of air is expressed in kilograms and represents the mass of air entering a cylinder when the piston is at bottom dead center, under standard air temperature and pressure conditions. Let's immediately take a look at how to calculate it. The formula to understand to calculate the mass of air entering the engine without considering supercharging is to multiply the standard pressure by the volume of the engine, dividing everything by the product between the number of cylinders of the engine, the ideal constant of the gases, and the standard temperature. Let's analyze this formula in detail by breaking it down into each of its elements. We have mnom, the nominal air mass of the engine cylinder at standard temperature and pressure when the maximum piston volume is reached at bottom dead center. PSTD, standard pressure, which equates to 101.325 kilopascal. VD, the volume of the engine expressed in cubic meters. NCYL, in our case, is worth 4 because it represents the number of cylinders of the engine represented in one of the previous images. RAir, the ideal gas constant, valid for clean air entering the intake manifold, is 287.05 joules, 2 degrees Kelvin per kilograms. It will be easier to replace joule with its extended form pascals by cubic meter. So, pascal by cubic meters per Kelvin degrees by kilograms. TSTD, standard temperature, which equals 288.15 degrees Kelvin. Let's try to apply the formula we have just seen to a Golf 4 TDI 1.9 liter 90 horsepower. Now, let's look at an air quantity map and understand how it works. The map in question, according to the engine speed and the milligrams of fuel to be injected for each cycle, indicates the amount of total inlet air that can be entered for each cycle. Knowing that the compression ignition engine works in excess of air, thanks to these maps, it is possible to calculate the total mass of air it can bring into the cylinder, 850 milligrams. Consequently, with this map, it is possible to understand the mass of the exhaust gases recirculated by the EGR valve. We just need to get the difference between the total air flow entering the manifold with the actual amount of air entering the intake duct. Applying the formula we have just seen, using as reference 2,247 RPMs and 15 milligrams of injected fuel, we find a value of 424.8 milligrams entering the engine from the outside clean air, and we get 425.2 milligrams. So, we can say that the mass of exhaust gases reintroduced to the intake is approximately equal to the mass of air coming from the outside. Curiosity. This map can portion the exhaust gas reintroduced by the EGR valve or decide to limit its reintroduction as much as possible. Furthermore, the engine control unit, knowing the amount of exhaust gas air to be reintroduced, performs a mathematical calculation to determine the amount of fuel necessary to develop sufficient exhaust gas. Let's take a look at the map in question. Thanks to these maps, it is therefore possible to portion the operation of the EGR valve and consequently decide the amount of exhaust gas to be reintroduced into the intake. It should be kept in mind that if we want to calculate the actual amount of air that enters the intake duct, it is enough to calculate the previously seen formula, but in reverse. The total mass of air and gas entering the cylinder minus the air recirculated by the EGR valve. We applied this formula, considering the mass of the reintroduced exhaust gases equal to 375.2 milligrams. Now, let's move on to one last important factor: turbo lag. Turbo lag can occur as a result of the driver's rapid actuation of the accelerator pedal in engines with fixed geometry turbochargers. The turbo lag is characterized by a less prompt response in delivering the required performance compared to an aspirated engine, due to the operating principle of the turbocharger which needs a large exhaust gas flow rate to overcome the inertia of the own impeller and produce the supercharging effect of the engine. By definition, it can happen, for example, when we stop pressing the accelerator pedal while traveling and we have the minimum amount of fuel injected into the combustion chambers. The exhaust gases are therefore characterized by low temperature and pressure valves, and in this phase, the turbine does not work at its optimum operating point. Due to the insufficient energy input of the exhaust gases and the mechanical inertia of the turbine compressor system, the compressor does not reach sufficient rotational speeds to allow significant compression of the air intake. In this situation, the engine, which draws in uncompressed air, does not perceive the presence of the turbocharger. Therefore, a rapid demand for performance by the driver, implemented by rapidly activating the accelerator pedal, cannot be fully satisfied until the flow of exhaust gases reaches a flow rate sufficient to accelerate the turbine and the compressor connected to it. There are several systems to significantly mitigate the phenomenon of turbo lag, including the wastegate valve, multi-turbo systems, the variable geometry turbocharger. Here we are at the end of another video. In short, in this video, we have described and examined the flow of fuel to be injected with its driver wish. We have seen the formula for calculating the mass of air per cylinder normalized, and then concentrated on the management of the recirculation of exhaust gases, to finish with the description of the turbo lag. In the next lesson, we will analyze another strategy applicable to diesel engines: mass flow metering. Don't miss it. See you at the next step.